We go. So welcome back, everybody, for today's session of the Cardiff Analysis Seminar. Today, we're delighted to have Henrik Schumacher from Aachen, who will talk about self-avoiding energies for curves and surfaces. So without further ado, over to you.
Yeah, thank you very much, Matteo. Yeah, so it's quite likely that you haven't ever heard anything about self-avoiding energies. So this will be hopefully a really basic talk. And I just try to sketch what's known about that, why we want to do that, and how we do that. And in the end, it will be pretty much numerics, because I'm really interested in minimizing these energies and to see how the minimizers look like. Okay, but yeah, what's the original motivation? Yeah, so think about isotopies in space, about isotopy equivalence. You have some geometry like this curve on the left, and you want to simplify it without changing the isotopy class. And yeah, you want basically to go from the left to the right. It's isotopically equivalent, but it's simpler. For example, it has fewer crossings from this direction. So it's easier to analyze what you have. So think of a knot and you want to untangle it. That's the idea behind everything here. So I already mentioned isotopies. The mathematical definition is a bit subtle. So for smooth isotopies, let's just say it's path components in the space of smooth embeddings. In C0, so in the space of continuous embeddings, things are slightly more subtle, but let's just think about paths and path components in the space of embeddings. And slightly informally, well, what we are looking for is we have a starting frame and a final frame for a video, and we want to have something like a video in between that untangles this curve, and that also gives us a guarantee that the first frame and the last frame are really equivalent. Okay, so there are different various approaches how to do that. One way is to say, okay, so just think you have some ball of knotted wool and you try to untangle it. What you try to do is you try to pick strands and pull them apart. You really want to spread it out somehow, like, yeah, in order to see what's going on. And it gives you have the clue that spreading things out would untangle the knot. And yeah, so something more, a bit more fancy, a more fancy way would be to say, oh, I invent some energy, and when I minimize this energy along the flow that I apply to this energy, the knot or the surface is untangled. And these energies, well, they should involve something like a 2-point potential that's repulsive. And the quite natural choice is something like this, something like, which is like Coulomb-like. Coulomb potential would be alpha equals 1. We will see that alpha equals 1 is not strong enough. We need a larger alpha. Well, yeah, because we need it to be sufficiently repulsive. What we mean by that is if we deform a curve or surface so that a self-intersection emerges, then we want that the energy goes to infinity. Like if two strands of the curve meet, this singularity should capture that. Well, so one may ask, what's a good alpha for that? And in the case of curves, you can do a really simple experiment. I have two curves, gamma and eta, and they have a distance delta, and basically they are in such a orthogonal configuration, and delta is the distance between the curves. And you can write down what this distance integral would be, and you get 3 terms, 2 green ones, which are self-intersections of each curve with itself. You see here gamma and gamma, and in the middle that's a cross interaction between the 2 components of the curve. And the curves are really simple, so we can translate that into simple integrals of over x and y. And what we see is that red integral, it has to blow up with delta to 0. Otherwise, we cannot prevent a self-intersection. And for that, we require that alpha is greater or equal than 2. And the self-intersection terms, well, we cannot avoid them. They need to be finite, but this can only happen if alpha is smaller than 1. So basically, this idea is broken. It cannot work. Yeah? You don't find any alpha that does the job. But there is a way to mend that. And one way is the so-called tangent point energy, where you see in the denominator, there is something like a Coulomb potential, and you put something else in the numerator that becomes sufficiently small with a sufficient rate so that this integral can be finite for smooth curves. And what we have in the numerator is basically the secant between 2 points multiplied by some orthogonal projector. And there is a geometric interpretation to that. So here on the right, I drew such an orange curve. And we have 2 points on the curve. This is f of xi, and this is f of eta. And then we have the tangent at the point f of eta. And this tangent and these 2 points, they define a 2-dimensional plane. And within this plane, we have a unique circle that is tangent to the curve at this point and still contains this other point. And the radius of this circle is connected to this integrand. It's actually 1 over the integrand of the tangent point energy. And if you move this point eta, or f of eta, to the point f of xi, then this circle comes closer and closer to the osculating circle at the point f of xi. So this radius is the inverse of the curvature, or approaches the inverse of the curvature at the point f of xi. So this tangent point radius is some global notion of curvature radius. And so our tangent point energy has a representation like that. It's a double integral of 1 over the tangent point radius to the power p. And there's also a nice characterization of the tangent point radius in terms of reach. When you have a submanifold in Rn without boundary, and if you take the supremum of all tangent point radii of points on the surface, on this curve, what you get is 1 over the reach of the surface. The reach is the largest radius to which you can thicken the surface without self-intersection. So it's the thickest tubular neighborhood has the reach as its radius, slightly sloppily. So, and if you try to modify your surface so that you can make it, or your curve, thicker and thicker, if you try to maximize this thickness, then you actually maximize the reach, or you minimize 1 over the reach. And if you replace the integrals, the suprema by integrals, and you insert this power p, then you get the tangent point energy, which is something like an LP relaxation of the reach. So it's also tries in some weaker sense to allow for thicker and thicker tubular neighborhoods. Yeah, well, you can actually define these energies for relatively arbitrary subsets in Rm. The only thing you need something like a tangent plane, so that you have a projector. Then you can say for 2 points on the surface what the tangent point radius is. And if you have a fixed dimension, you can just integrate against the Hausdorff measures. And one can show that in a certain class of admissible sets, finite energy means really means that the set that we have is actually a C1 embedding, and it's even a slightly better, it's even C1 alpha, with the alpha that depends on dimension and the power P that we apply. And one can even show that if the energy is finite, then there is a certain Sobolev space that belongs to the surface. So one finds a parameterization with a fractional differentiability. So 2 minus n over p is in all cases larger than 1 and smaller than 2. So W as p, you really read it as functions, measurable functions, or parameterizations of, with s derivatives, with s fractional derivatives in some LP. And of course, the first question that one has when one defines such an energy, are there minimizers? And the answer is true if you at least bound the diameter of the surface. It's like with most curvature energies, if you scale the surface or the curve up, then the energy goes down, because curvature is something like 1 over this length scale. But if you don't allow the surface to blow up, then there is actually a minimizer of this energy in each ambient isotopy class, at least for closed surfaces. And well, it's more or less basically the direct method of calculus of variations. But of course, one use lower semi-continuity and compactness of lower level sets. And of course, one has to show quite difficult things about that first. But that tells us, okay, this is a meaningful optimization problem. Some closed surface in Rn, and we try to minimize its tangent point energy within its isotopy class. And well, how do minimizers look like? And theoretically, only one type of minimizer is known. That's the sphere. So within the class of embedded spheres, the round sphere is always a minimizer.
I'm sorry to interrupt you. At some point, we started hearing very, very far. I don't know if something happened to the microphone. Somebody has been writing.
Well, yeah, that's okay. Let me reconnect the mic. Wait a second. Is it on?
Yeah, much better.
Yeah. Okay. That's a weird thing that happens every 20 minutes.
Thanks.
So please tell me if it happens again. Okay. So basically we have no idea how minimizers look like. And if you don't have an idea, well, a good thing is to do some numerical experiments. So how would we do that? And the classical approach is discretize and optimize, or some people say discretize and Newtonize. The problem is we have the surfaces form an infinite dimensional manifold. And well, in order to put it onto a computer, we have to turn it into some finite dimensional problem. The classical thing is replace smooth surfaces by polyhedral surfaces, and then like triangle surfaces. And then the degrees of freedom are the vertex positions. Then you formulate a discrete energy, and then you just apply. This is, yeah, just apply finite dimensional optimization techniques to find minimizers. But in fact, it's all not that easy. For example, I told you that if the energy of a surface is finite, then the surface has regularity C1 alpha, especially C1, but polyhedral surfaces don't have C1 regularity. So if we really want to use polyhedral surfaces, and I do because they are easy to handle practically, then the tangent point energy is always infinite. So one has to sort of make up a discrete tangent point energy that does reasonable thing. And the second issue is recall how the energy is defined. It's defined by such a double integral. Well, and double integrals are much more expensive than single integrals. And so even evaluating the energy is really costly. One has to do something about that. And the third issue that you stumble upon is it's not that easy that you can just take a black box optimization tool for finite dimensional optimization because it will just perform super badly. So there is when you refine the discretization, there is an increasing ill conditioning, and one has to do a clever thing about that in order to avoid it. And I'd like to quickly address all three of these topics. First is how to discretize the energy. And this is actually rather straightforward. As I said, you take, instead of surfaces that are smooth, you take simplicial meshes, triangle meshes, or polylines. And the energy involves the orthogonal projector, so the projector onto the orthogonal complement of the tangent space. Well, for a polyhedral surface, you don't have a tangent space everywhere, but you have it on each facet. There's a unique, the facets are flat, so there's a unique projector for each simplex. And instead of an integral, you apply a midpoint rule. And what you do is S and T are simplices of the surface. You replace the integrals by double sums. You weight them, of course, by the surface area of the simplices. And you just plug in the facet midpoints and this constant projector into the tangent point kernel. Well, how does this look like in practice? For curves, for example, here we have a smooth curve. And we just inscribe a polyline into it. Then for each two line elements, S and T, well, we can just take their length. That's these Hausdorff measures over here. We can take the midpoints and the secant. And this is the normal space to this line element here. We have an orthogonal projector. We take the secant and project it orthogonally. And then we have everything we need to define our discrete tangent point energy. For surfaces, it's similar. When we start, first we start with a smooth surface, then we sprinkle some points over it, connect them by triangles. And then for two triangles, we have, again, a secant between the midpoints. We have a normal space. We project the secant to the normal space. And again, we have all ingredients that we need to write down this double sum. Well, is this actually meaningful? The simple answer is, I don't know. So it works in practice. But for example, what we cannot show at the moment is when we compute discrete minimizers, we cannot prove that they are really close to smooth ones. But what we can do is we can take a decently smooth surface and we can discretize it. And we can see if we are at least able to approximate the true tangent point energy. So in this table, E is the true tangent point energy for a certain parameter P. And what I show in this column is the relative error between the two true tangent point energy and the EH is the discrete one. And I just increase the resolution by splitting triangles further and further. And what you see here, this error goes slowly down to, well, hopefully 0 in the end. But you also see here already that the time you need to just compute the energy scales really quickly with a number of triangles. Basically, it scales quadratically with the number of triangles that you employ, which is really bad. If you want to have a rather accurate result, you have to spend quite a lot of time. And that's something I'd like to address later, but at the moment, I'd like to talk a bit about Riemannian metrics on the space of embedded surfaces. And this is joint work with Philip Reiter. We wrote a paper that addresses this for another self-avoiding energy, the so-called Möbius energy, but the story is almost the same. Well, usually what you do when you have a discrete energy or also a smooth energy, what you try to minimize it, you just try to run the L2 gradient flow. That's sort of the standard thing. Yeah, what you do is you sort of compute the differential of the energy with respect to the surface and test it against other functions, and then you can say how the time derivative of the surface should behave. But what you end up is a nonlinear, non-local parabolic partial differential equation. And also it has fractional order somewhere between 3 and 4 typically, or between 2 and 4, but mostly it's greater than 3 already. And that's pretty difficult to simulate. And there are a couple of reasons for that. If you have some concentration phenomenon, then the L2 gradients become pretty large. So you need to take small steps. And a second issue is that you always have a bit of noise in your numerical computations, just because of rounding errors. And these errors tend to be amplified if you don't do it cleverly. And even if you do that cleverly, the flow is really, really, really slow. And here's some example. So this is some noisy trefoil knot. And if I apply 10 steps of L2 gradient descent, you see it almost hasn't changed. But what happens is pretty similar to, for example, heat flow. You see some local smoothing. Yeah? You see high frequencies are damped down, and even more so if I apply 10 further iterations. But still, like overall, you don't think that the geometry has changed much. So you're still far away from the minimizers. And the major reason is what I already said. The L2 gradient is really sensitive to concentration. So what I have here is some orange curve that is knotted. And the L2 gradient is just a vector field along the curve. And I plotted this vector field. And you have also to think about of L2 gradients like forces. So the energy is some accumulation of 2-point potentials, and the L2 gradient is some accumulation of the respective forces. And of course, these forces are large in areas where things come close, where the knot is rather tight. And so this is just chaos here that tells you, well, if I move the curve in that direction, I really have to take small steps. Otherwise, I have the self-intersection or tunnel through myself, as the curve tunnels through itself. And the second issue is if I just apply a really tiny amount of noise to the curve, like here, really the curve is almost the same visually. You barely see any information. The L2 gradient gives you no information what to do about the curve in the large. Locally, it's always a good move to remove the noise, but it's quite chaotic. So you can imagine that an optimization method that gets handled this as a gradient won't work pretty well. But there is some solution to that. And I already said that these energies have some sort of a natural space, in the sense that the tangent point energy is finite if and only if the surface or the curve has a certain regularity in some Sobolev-Slobodetsky space that you have to read as fractional derivatives in LP. I don't want to write down further how these spaces are defined. It's just something between W1P and W2P. One can really define them via interpolation, for example. But just think about it. The differential is a mapping from WSP to the dual space. The dual space is something like W minus SQ, where Q is the dual of P. And by this reasoning, the differential is a differential operator of order 2s. And that's what you lose when you apply the derivative to a surface. And well, that's why noise is such an issue here. Yeah? If you have something noisy and you apply derivatives to it, it gets even more noisy. And so the idea that we had is, well, maybe we should invent a Riemannian metric that really fits well to this Sobolev-Slobodetsky space. And it started all with a heuristic. Basically, we said something like P doesn't matter that much for Sobolev space. What's important is the S, the differentiability. So let's take the Hilbert space that is sort of closest to the energy space. In this case, this is HS. And then let's take the standard product there, or some meaningful inner product on this page as HS. And you automatically find out, oh yeah, something like the fractional power of the Laplace-Beltrami operator on the surface. That might be a good choice. Yeah? Apply the operator and then an L2 inner product that yields a inner product of the right order. Well, actually computing fractional powers of the Laplacian is computational expensive. So we tried something else. There's this notion of Gagliardo inner product that is defined by double integrals and differences of functions. And we also apply a first order differential operator. This is also a scalar product on HS, on the Sobolev space. But it's computable, because we have to do basically the same thing that we have to do for the energy. We have to compute double integrals. And via these double integrals, we also see, oh yeah, this is really similar to the energy. That seems to fit quite well. And this allows you, so we have a inner product, and this allows us to define gradients by saying, if I want to compute the gradient U, I test the differential with smooth test functions V, and I do so also with U, but I apply this inner product when I test it. So for the L2 gradient, this would be an L2 inner product. We use this HS inner product. And of course, we were aware that this Sobolev space is not a Hilbert space. So P is not equal to 2. So it's not really a Riemannian metric in the strict sense of a Riemannian metric. It doesn't identify the tangent space with its dual tangent space. But this notion of gradient at least provides a Lipschitz continuous vector field. And that's nice, because Lipschitz continuous vector fields by the Picard-Lindelof theorem, they are easy to integrate. And that's what we explored. And that's why it works so well, what we do. And here's a direct comparison. So that's the trefoil, the noisy trefoil from before. On the left, I will show you a couple of steps of the L2 gradient flow. And on the right, it's the fractional Sobolev gradient flow. And I do it step by step, because you see that on the right already it works just much better than on the left. After 10 steps, we are basically done. We can add 10 further steps. We just needed 20 steps, or 10, to reach the minimizer, while the H2 flow, well, it hasn't finished yet. And I showed you before this image of the L2 gradient. So I also like to show you how this fractional Sobolev gradient differs from this. So this is the HS gradient. And when you compute the gradient, you basically apply an inverse of the fractional Laplacian, or you apply an inverse of a certain fractional power of the Laplacian. That means you smooth out the L2 gradient. And that's what you see. This is really like, you still have a bit of concentration here in the middle, but yeah, you might get the idea. The curve moves a bit more coordinated. And then we applied a further trick. We actually use a different metric, and the gradient of this metric looks like this. And the idea behind this is, well, here it's really entangled. We shouldn't move too much here, but over here we have a free loop, so to say. This is allowed to move quite quickly because it won't run into another piece of curve over here. So we try to construct a metric that encourages movement around here and penalizes movement here where it's entangled. And I'll show you soon how we define this metric, but I'd like to show you also that this metric also involves this fractional inner product. So computing the gradient means smoothing. And this means this is also why noise is not that much an issue. You see, well, applying noise does change the gradient, but it's still qualitatively, it stays the same. So small movement in the middle, large movement where it's free to move. Just a quick look on how we define this inner product. So you just, when you have already an inner product, you can just add something which is positive semi-definite. And what we did is we add a further Gagliardo inner product, where we have some function differences here, but we apply an additional weight, and this is the tangent point kernel again. And this becomes large basically everywhere here, and it's small everywhere here. So the norm of a vector field along the curve is small only if the vector is not too long in this region, and that's what we wanted in order to have small vectors here, large vectors over here. Well, of course, you want to see that in action. So I prepared a video for you. And I have to switch the window for that. Do you see it now?
Yep.
Okay. So typically it runs a bit too fast, so I slow it down a little. And now I start the video, and that's what's basically happening. So, and now you also see, I run it again. So now this is almost the configuration that I showed you before. It was just, the image was just one half of the curve. And now you see how crucial it is that the curve is allowed to move at the ends here where it's free, because we have to pull it through this other loop. And yeah, by the way, so the initial curve was proposed by Friedman, He, and Wang, who worked on a different, on a similar self-rewarding energy, but they said, well, it's quite unlikely that you will be able to minimize, that you will be untangle this unknot by just minimizing an energy. So they really try to construct something you cannot untangle this way. Well, we can actually. Okay, back to the slides. Okay, so this work is already, I don't know, 2 years old. So we managed to do that for curves. These curves had 1,600 vertices. So these double integrals were not that super expensive. But then we went on and tried to do that with curves, with surfaces. And for surfaces, you need many more triangles to make them look smooth. That's just the curse of the dimensionality. And the method that we used there, just doing all the double sums, and we also have to solve a dense linear system in order to compute the gradient. That's just not feasible for curves, for surfaces, sorry. So this last third of my talk is about joint work with Keenan and Christopher Yu from the Carnegie Mellon University in Pittsburgh. And here we really tried the basic problem are the double sums. So basically what you have to do is, you enumerate all your triangles. You have a triangle surface or also polyline, then S and T are just the line elements. But let's say we have a surface at the moment, S and T are triangles. For each triangle, you have some number. You can form a matrix of it, and the energy is basically take the matrix and multiply two weight vectors against this matrix. And typically, you would expect if the matrix has size n times n, well, you have to compute n times n entries, and n you have to think is in the 10,000s or millions, maybe. This A might be a really large matrix, and we want to compute basically the sum of all entries in this matrix without ever computing each entry in the matrix. That's our goal. And I tried to show you why this is possible. I cannot explain you how exactly we do it, but the idea is the following. Oh, now I have again a curve. Sorry, I said it's a surface. Now we have a curve. And this matrix for this curve, this looks something like this. Yeah, this is the diagonal. There it's pretty hot. High colors, high tangent point energies. That's because of all these wiggles, 2 points that are close on the curve are also close, have typically large tangent point energy. But if you go outside, here are points that are more distant. There are a couple of bright spots like here. One of those bright spots probably belongs to approximately this crossing, another bright spot to this one, and the third to this crossing. So you see something in this heat image or in this matrix plot, you see some characteristic behavior of the curve, for example, or some threefold periodicity, for example. Well, but so we want to sum over all entries in this matrix. But let's stick for a moment with a small portion of this matrix that belongs to 2 pieces of the curve. Let's zoom into it, and then we cannot see anything because we first have to raise the contrast. That's what I did. And you see here, well, there seems to be some structure in the matrix. There are these small ripples. They are due to these many helices over here. But now we may ask how much information is actually contained in this matrix block. And how do you figure out how much information is contained in a matrix? You apply a singular value decomposition and you plot the singular values. And what you see is, this is, say, 1,000 by 1,000 matrix. But the significant singular values, that's the first 3 or so. Like this huge matrix contains almost no information. So there should be a way to sum all the entries without computing each entry. And the reason for that is that this matrix is generated by a kernel function, and this kernel function is rather smooth. So if you have 2 portions of the curve that are relatively small, then you can say, oh, the corresponding matrix block is almost constant. And then you can do this summation over all entries by just taking this constant and multiply with the sum of the weight vectors. And this would take you a number of entries of the matrix flops. Yeah, so if the matrix is an n times n matrix, that takes you n times n flops. While this takes you only n plus n flops. And for large n, this is really much better. And now the question is, how do I find portions of the surface, i's and j's, of the curve, so that this approximation is actually valid? And there's a rather simple admissibility condition that you have to fulfill. You take the convex hulls of these points within these portions, take their minimal distance, and compare that to the diameters of these two clusters or portions on the surface. And if the diameters are small compared to the distance, then you typically are allowed to say this approximation is fairly valid. And what you do then is you take this overall matrix, you apply some clever technique to decompose the product of the curve with itself into these small blocks. And you get two types of blocks. The green ones, these are the good ones, they fulfill the admissibility condition. And basically you can say, oh, we can replace the whole matrix block by just one number. And we just compute it in the middle. We replace the matrix block by the average. And then there are a couple, but few red blocks here among the diagonal. Those are the ones you cannot compress this way. You just compute every interaction in these blocks. But basically, you get something which is concentrated along the diagonal that's costly, and all the green ones, they come rather cheap. And I just like to mention that these are techniques from, for example, computer graphics, where you take your geometry and use some hierarchical clustering technique to find small patches on curves or surfaces, and to figure out what would be a good block decomposition. This is quite complicated. I don't like to go into detail, but I would like to show you what the effect of this method is. Basically, just for computing the energy, if you have n triangles or n edges for a curve, just computing the energy naively would take you n squared time units. And due to this hierarchical clustering, there are many binary trees involved. That's why you can trade one n for a log n. And in computer graphics, they say log n equals 10. So this is basically O of n. And we actually see that. So this is the old table I've showed you with the old timings and with the old errors. And this is now for a compressed version of the discrete energy. It's not just taking the average on each block. It's slightly more sophisticated. But what you see is the average is the relative errors are almost the same, if not even better. And the timings are much better. So for small, for few triangles, that's actually not true. It takes longer, but it catches up quite quickly. Yeah, for 20,000 triangles, you have already a speed of a factor of 10. And for 300,000 triangles, it's a factor of more than 100. And that's quite astonishing. That's what's crucial if you want to use these energies for any applications. And nobody would use them if you cannot implement that in an efficient way. Yeah, this is once more a plot. It's basically the old table, but now on the plot, you actually ask for how much time do I have to invest to get a certain accuracy. And the orange curve tells you, oh, in order to improve accuracy, so in order to make the error smaller, you have to invest quadratic time, while if you do the naive thing, and if you do this clever, compressed, fast multipole approximation that I tried to explain, the cost rate is much better. Well, why did I tell you all this? Well, this was the only way for us to create the following videos, and I don't know how much time do I have left. Basically, I have only a couple of videos to show, several ones. So let's see what I have to do. And yes. So do you see this bluish figure 8 knot?
Yes.
Okay. Okay, this is not a knot anymore, it's a surface. Yeah, we thickened it and we cut it here and we included a couple of caps. And actually I can make it faster. So, and what we do now is we use this fancy discretization and also some trick to evaluate the gradient, and we apply a standard gradient descent technique for this Sobolev gradient. And we obtain this video. I think the surface has about 10,000 triangles, and that was something that my computer couldn't do anymore without this compression technique. Of course, this is not a live video. I don't know how long it took, maybe an hour or two. I guess we can make it faster in the future. This is just every step of this optimization routine is now one frame in this video. And now let's see what happens. And you see it's, oh, it was way too fast. So let's try it again. Isn't it beautiful? And of course, it's a topological sphere, so you really want it to shrink to a sphere in the end. So that was one of the simple examples. Then there's, for example, this one. What you see here is a double torus, and obviously this one is non-trivially interlinked. Obviously, yeah. So let's see what happens here. And now we see, oh, well, it's sort of a double torus. But I was really surprised that the optimization didn't stop here, but went on, and we got something like this. And who's familiar with the Willmore energy? So the Willmore minimizer for a double torus looks a bit similar. There are these Lawson surfaces. It's actually not known whether they are the global minimizers. I think, I'm not sure. They have also this threefold symmetry. And look similar to this one. Okay, here's another one. This was actually motivated by Keenan found some paper that defined the tunnel number of a knot. What we see here is again basically a figure 8 knot, but there were 3 tunnels attached to it, or handles. Here's a handle for each crossing. There is a handle attached here. And the crossing number of a knot is the smallest number of handles that you have to attach, such that the knot becomes a trivial handle body. And I'm going to show you that the handle number of this knot is at most 3. Let's see what happens. So you see, it's basically a wire model of a cube, thickened in some way. That was really surprising to us. Nicely symmetric again. We didn't expect that. Actually, we didn't expect that this could be untangled. Yeah? And so we constantly try to break our method. So what we did next was we took a trivial, almost trivial knot, the trefoil knot. It's the second simplest knot that you can imagine. It's not trivial. But we made it hard by adding some loop over here and attaching it to this, to the rest of the surface. But that's what happens when we minimize the tension point energy. So this is an old friend. This looks again similar to the Lawson surface. So this is, it's quite likely that in the space of the it's a two-handle body in the isotopic class of the two-handle bodies. This is probably the global minimizer. We cannot tell. Having seen these videos, one could expect something like, oh, everything is a simple handle body. It's actually not true. We have another example. It has a threefold symmetry, and it's called the Thurston tripos. I forgot what the purpose of the tripos was, but it was guaranteed that it's not a simple handle body in terms of isotopic class. So let's see what happens here. Yeah, so it's basically a sphere with a couple of snakes attached within the spheres. And you see the formation of a couple of trumpets on the boundary. And basically it gets tighter, but it doesn't resolve to a handle body. We don't know if this is a global minimizer or not. We were just surprised that our method worked that well with it. Yeah. Well, I have another video which was basically we expect people to ask us, why don't you just use a Coulomb potential and L2 gradient descent? This is a bad example. So this is, again, we haven't rendered it nicely. This is an example, again, of this entangled double torus. And here we really try to minimize just a Coulomb potential. I forgot which exact power we used. We tried to fix the area of the surface and minimize. And what happened is basically the surface is blown apart. So this is why you need to have this regularizing term in the numerator of the energy. And the final example I'd like to show is, I think that's the newest one. I'm not sure. I see. It's a QuickTime video, that's why. Okay, that's the newest example that we have. It's not nicely, smoothly rendered, so you really see the triangles, see how many triangles. That's what this example does. Maybe this was a bit too quick, but I cannot slow it down in this viewer, I'm sorry. Yeah, well, that's basically what I'd like to show to you. So thank you very much for your attention.
Thank you very much for the talk. So, questions for the speaker?
First, thank you, Henrik. That's so impressive. So,
Thank you.
what you've done in the meantime. So, so first, so you said, I think around page 23 or something, that there's something what you'd like to prove, but what you can't prove. Maybe can you say a bit on this, or?
Well, that's
about
yeah.
that you have an actual minimizer or something. I forgot to write down. So.
Well, yeah, that's always so. That's the issue with numerics. Yeah. So in order to make things fast, you have to cheat somewhere. You have to break the rules. And what we do is we minimize within a space that's not in the domain of the energy. But we believe that the finer we make the discretization, the less severe is this crime. So our working hypothesis is when we compute these discrete minimizers, they will be increasingly close to a true minimizer when we take more and more triangles. But we cannot even show that there are minimizers in the discrete setting, for example. It would be way easier if we knew that the discrete surfaces that we use were within the energy space of the smooth energy. But they aren't. We made a decision there. It's basically, we would need C1 surfaces in the discrete model. And modeling C1 surfaces is really difficult. People do that, for example, in CAD applications, in design. But as soon as you want to do finite elements, some numerical computations, all these nice surfaces are typically taken and discretized to triangle meshes or to TET meshes, to these discrete meshes, because C1 surfaces, discrete, finite dimensional spaces of C1 surfaces are a pain to handle numerically. So,
but you do anyway. Thanks.
Yeah. So it's just we really, one calls this, we apply a crime, this variational crime. We minimize in a different space, a different energy, but we still hope to get essentially the same minimizers. Of course, well, there are other similar energies, for example, surface area or Wilmore energy, where one applies the same techniques and it works well, and partially one can show why it works well. So we are a bit ahead of time. We have a method, but we cannot, it seems to work, but we just cannot show that it works, not at the moment.
So more questions for this speaker?
Maybe I can ask something. This is a naive question. Can you use these kinds of methods to prove theorems in topology? Like,
that was actually the idea behind the Möbius energy. I only mentioned it. So there are papers by Friedman, He, and Wang, and they tried to prove the Smale conjecture with it. The Smale conjecture has various formulations. One of them is the space of unknots is isotopically equivalent to the round circles. So there is an isotopy or a smooth retract or a continuous retract of the space of all embedded unknotted circles to the round circles. And the idea was, if we had an energy that has only round circles as critical points, then the flow would do exactly what you want. Yeah, you would get a motion towards this retract. But nobody has ever been able to prove that. What's proven, and that's already fascinating, if you do that in the plane for the Möbius energy, not for the tangent point energy, for curves in the plane, they cannot be knotted, but there are no critical points other than round circles. So whatever embedded curve you take in the plane, you run this flow, you will always end up in a round circle if you wait sufficiently long. That's already a pretty cool thing, isn't it? And well, people really wanted to use that for topology. Like, for example, there is a proof that in each isotopic class, there is a minimizer. So we have a new knot invariant. Yeah? Knots are isotopic classes. The minimal tangent point energy within a knot class is, of course, a knot invariant. And people have shown like their bounds so that this tangent point energy bounds, for example, crossing numbers of knots, other topological invariants. Of course, this is a topological invariant that's hard to compute, the minimizer. But that's what we try to do here, right?
Thank you.
Maybe I can follow up on this. So if you modify your energy by something that punishes not being a circle, like the Coulomb energy, like this. So in the normal bundle, you have this Coulomb energy which measures being away from a plane. So you can force your knot to move into a plane, and then you apply your previous your just mentioned result that you have in the plane, that you have this property that only the circles are minimizers. Can you use some modification to your energy like this to do this?
Well, this feels a bit like squeezing the knot into the plane. That's what topologists do all the time, because they tend to just project it into the plane. Then they get a so-called knot diagram, and then they work with the crossings. But crossings are evil. Well, these are self-intersections, so the energy is infinite. But people are working on renormalizations, like a colleague here in Aachen. She asked, what happens if you cut out the intersection? What happens if you modify this energy? So yeah, there is a way to work with that, but it's not as easy as just pressing everything in the plane.
More questions for the speaker? Doesn't look like to be the case, so let's thank the speaker again.
Thank you.